Okay, our next video, number 6, I believe, in our series on biomechanics of jumping for performance here, is also a study on vertical jumping. Similar to the previous study, it's also getting at one of the common things that we observe in that people jump higher when they swing their arms, or people tend to jump higher when they're allowed to swing their arms. Similar to the previous study where people tend to jump higher when they're allowed to do a counter movement versus a squat jump. And people also tend to jump higher when they're doing a counter movement jump and when they're allowed to swing their arms when doing the counter movement or throughout the counter movement jump. Again, here we shouldn't be satisfied with just observing that people uh, jump higher when they swing their arms. So let's get everyone to swing their arms when they jump and improve performance. That's important. That's a good thing to observe and to include in our best practices for training people for jump height and for coaching effective jumping. But from a biomechanics perspective, we shouldn't be satisfied with that observation. We should dig into the nitty gritty details underlying why people jump higher when they swing their arms. That's how we can really learn more biomechanically about what's underlying the improvement in performance when people are allowed to swing their arms. So extending on where we left off of last time, and trying to explain why people tend to jump higher when they do a counter movement jump versus a squat jump. This paper, the previous paper, the Anderson and Pandy paper, I think gives a pretty compelling argument that it's probably not from increased storage and return of elastic strain energy in muscles and tendons. That doesn't seem to be, at least based on this study, a terribly plausible argument for why people tend to jump higher with a counter movement jump. So let's look at what was really different between squat jumps and counter movement jumps. One thing that they don't spend too much time on in the paper, because it wasn't really a goal of the paper, but one thing they don't really spend too much time on in the Anderson and Pandy paper was this result right here that I have highlighted under their results, where the liftoff times, or the time that you spent doing the jump with your feet on the ground, was about 1 second for the counter movement jump and about half a second for the squat jump. So people were roughly, spending twice as much time on the ground executing the jump, doing the counter movement as they were doing the squat jump. And I think that's a key factor for why people tend to jump higher with a counter movement than with a squat jump. And why is that exactly? We covered this briefly several lectures ago. I forget when exactly. It's been at least a few lectures. But the source of my thinking there is this first relationship in my document here, the impulse momentum relationship. And this says if you have a mass and you want to move that mass, if you apply a certain force to that mass, such as the force between your feet and your ground when you're jumping, the average force that you generate times the amount of time that you're generating it, times the amount of time that you're generating a non-zero force. You take that average force times the amount of time that force is being generated, and that product there, average force times the duration of the force application, or delta t, that gives you the impulse of that force. Okay? That impulse from basic physics equals the change in momentum of the mass that the impulse is applied to. Okay? Mass is more or less constant in a movement like this, in a short duration human movement. So we take m, factor m out here, and we get that F delta t equals m delta v, or that impulse equals mass times change in velocity. Okay? Now, let's apply this to the takeoff phase of jumping, or the ground contact portion of the jumping motion. F here would be the average force that we generate between our feet and the ground when we're performing the jump. Delta t here would be the duration of time that our feet are in contact with the ground and we're generating this force. M here would be the body mass. And notice here all that's changed from my top equation to my bottom equation is that delta v has become v takeoff, or my vertical velocity at the instant of takeoff. Okay? Now what happened there? Remember, delta v here is the change in velocity during this change in time, or the change in vertical velocity while I'm performing the jump. Okay? Whether it's a squat jump or whether it's a counter movement jump, my center of mass initial vertical velocity is zero, right? I'm either starting from standing still upright in the case of the counter movement, or I'm starting from a static squat in the case of the squat jump. But in either case, my velocity starts at zero and then increases to whatever my takeoff velocity is. Okay? So delta v here, in the case of a jump, is your takeoff velocity minus your initial velocity at the start of the movement, which is just zero. So it's takeoff velocity minus zero, or just takeoff velocity. Okay? So what this says is that if I then divide both sides here by body mass, fuss with my equation editor a bit here, divide both sides by body mass to get v takeoff by itself, and I see that I can increase my takeoff velocity if my body mass is constant, which is roughly constant during a jump. It's not like during the 1 second jump you're going to be changing your body mass appreciably. I can increase my takeoff velocity by doing one of two things or a combination of two things. I can change the average force that I'm producing, or I can change the duration over which I'm producing that force and averaging that force. Okay? So all other things being equal, like if you keep your average force constant, but you generate that force for a greater amount of time, like if you spend more time with your feet on the ground generating that force, that's going to produce a greater impulse, which is going to translate to a greater takeoff velocity of your body mass when you leave the ground. Okay? So that is why I think spending a lot of time in contact with the ground, roughly twice as much time in contact with the ground with the counter movement jump versus the squat jump is a big reason why people tend to jump higher when they do the counter movement jump. You're simply on the ground for a longer amount of time, to generate forces, possibly more time to generate even greater forces with your muscles and with your feet against the ground than you would in a more brief squat jump motion, resulting in a greater takeoff velocity. Why is takeoff velocity good? Because then we're airborne, and this translates directly to an increase in the peak height that the center of mass gets to. And there's mechanical and energetic underpinnings for that too that we'll cover a little bit later today. Okay. So I think that's a big factor in why counter movement jump height is typically higher than squat jump height. You just simply spend a great deal more time with your feet against the ground, generating ground reaction forces and resulting in faster takeoff velocities. Okay. So what does that have to do with the current paper? That was about the previous paper. Regardless of what you're looking at, if different types of jumps or different techniques for performing the same type of jump, whether you swing your arms or not, whether you jump this way or that way, in order to jump higher, the jump has to do one of several things. There's very few ways at the level of like the whole body here. If I'm considering the whole body mass, there's not all that many ways that a change in technique can increase jump height. And I kind of summarized them here in my previous document. If I have the goal of maximizing the height that my center of mass reaches above the ground, there's really only two ways, at least at the whole body level, if I'm just considering the whole body mass, not here dealing with like individual joints and muscles and stuff like that, just the goal of maximizing the height of the center of mass above the ground. There's two things I can do to increase the height that I get to. I can increase the impulse that I generate against the ground. Okay? Like I just described, I can do that through increasing the duration of ground contact and or through increasing the average force that I generate against the ground. Or I can increase the height of the center of mass at takeoff. Okay? Some combination of these things will result in an eventual increase in jump height. Okay? Now, why is this necessarily the case? Well, the first part here, the part about increasing the impulse generated against the ground. Okay? That again comes from my impulse-momentum relationship, where there's a direct relationship between the velocity that I leave the ground with and the impulse that I generate while my feet are on the ground. Okay? So greater impulse, whether it's from a greater force or a longer contact time or some combination of these things that just overall results in a greater impulse, right? Like if you increase duration or delta t by a lot and decrease f a little bit, you could feasibly end up with a greater impulse, depending on how much delta t increases and how much f decreases. Or you could increase f a lot and decrease delta t and then still end up with a greater impulse. But in practice, in reality, you tend to see things where f stays about the same and delta t increases, and that's how people end up reaching greater heights. So there's lots of ways to do this in theory, but in practice it tends to be from an increase in delta t while keeping force relatively constant. But that increase in impulse will directly translate to an increase in takeoff velocity, and mechanically, why is that a good thing? Once I become airborne, I'm basically stuck. I've basically already done everything I can to dictate how high my center of mass is going to get. This is because once I become airborne, there's one and only one force acting on me, and that's gravity. And I can't control gravity. I'm under the influence of gravity. It doesn't matter how I move around now, gravity is going to dictate what happens to me. Once I leave the ground, I have a certain velocity and I have a certain height that I am above the ground. My center of mass is a certain amount of distance h above the ground. Okay? That velocity that I leave the ground with endows me with a certain kinetic energy from this equation, energy of motion. And that height that I leave the ground at endows me with a certain amount of potential energy, of energy due to how high I am above the ground. Okay? Now, once I become airborne and gravity is the only force acting on me here, then conservation of mechanical energy holds, right? So if, for example, if I'm comparing how much mechanical energy I have at the peak height of my jump versus how much energy I have at the takeoff portion of my jump, right as I leave the ground and as my ground reaction force stops acting on me and as gravity takes over and is the only force acting on me, I can have different amounts of potential energy versus kinetic energy at those times, but the total sum of both of those types of mechanical energy, the potential energy plus the takeoff, has to be the same throughout that entire airborne phase. Okay? At takeoff here, I leave the ground with a certain amount of potential energy and a certain amount of kinetic energy. Okay? So I could sum those two quantities up to equal my total mechanical energy. Okay? As I'm moving through the air there after I take off, how much potential energy I have at any particular time will change, and how much kinetic energy I have at any particular time will change. But the sum of these two things, the total mechanical energy of my center of mass, does not change. I can shift around how much is potential and how much is kinetic, but the sum of them has to stay the same. So when I get up to the peak, for example, height of the jump, I have a certain amount of potential energy and I have a certain amount of kinetic energy. And I can't say exactly how much as a general rule, but I can say that the sum of my potential and kinetic energy at that time is still equal to the sum of potential and kinetic energy at takeoff or at any other particular time in the jump because of conservation of mechanical energy. Now, then for each of these terms here, on the next line, I've just substituted in my specific equations up here, the equation for potential energy at the peak, so mass times gravity times my height at the peak, plus the equation for kinetic energy at the peak, 1/2 times mass times the square of the velocity at my peak. Okay? Then on the right-hand side here, I've done the same thing. I've got the potential energy at takeoff, which is from my height at takeoff, and the kinetic energy at takeoff, which is from my velocity at takeoff. Okay? Now, when I'm at the peak height of my jump, my velocity in the vertical direction is instantaneously 0, and I'll give you a video example showing you why that's the case in a little bit. So this guy goes away. Okay. And I'm interested here in determining the peak height that I get to. So I'm going to divide both sides of this equation by m, by body mass, to get m out of the way. Then I'm going to divide by gravity, because I want to get h peak, or the peak height here by itself. So that g goes away. Divide this term by g. And then I get a divide by g here over on this guy. And then just for cleanliness, let's move v takeoff here up to the top, just for appearance's sake. So turns out that my peak height that I get to is going to be my height that I take off from, my height of my center of mass, plus a squared function or a quadratic function of my takeoff velocity. Okay? So this illustrates two important things. I can get to a higher eventual height if I increase how high I am from the first place. If I increase my height of my center of mass during the takeoff phase of the jump, then I'm kind of starting off with an advantage here. I'm already a little bit higher above the ground in terms of my center of mass, even though I haven't left the ground yet. And 2 here, since the takeoff velocity is squared in this equation, every tiny little increase in impulse here, which translates linearly to an increase in takeoff velocity, is going to get me an exponentially larger increase here in peak height, right? Because that v squared, that velocity, that takeoff velocity term is squared here in my equation for my peak height that I just derived from conservation of energy. Okay? So just a fairly simple mechanics explanation for why this is the case up here. Why these two factors are the single, at least at the whole body center of mass level, the only determining factors for how to increase jump height. You can either increase your takeoff height, which is effectively your initial potential energy, or you can increase or you can increase your takeoff velocity, which is effectively your kinetic energy at takeoff. Okay, no real other ways, at least at the center of mass level, to increase the height of the jump. So when you're increasing jumping performance in the form of peak height, one or both or some combination of these things that results in an overall increase in the peak height necessarily has to be going on. Let me give you a video example here of what I'm getting at with some of these things. So I'll pull up my video here quickly. Photo booth. Okay, let's say, for example, let me just grab something in the room here. I'll just use my charger here for my Nintendo Switch. Okay, let's say that my goal is to generate a force against this charger here that shoots it as high into the air as possible, right? I'm going to try and throw it as high as possible. Okay? I'm not going to actually throw it because the ceiling is kind of low and I'll hit it and probably break my thing. But just conceptually think of trying to throw this thing as high in the air as possible, or just more generally, what mechanics while my hand is in contact with it affect the height that it's going to get to when I release it with my hand when it comes off my hand. Okay? So let's say I want to get the center of mass of this thing as high as possible. Okay? If I release it right here, like down at Giants level on my shirt, it's not going to go all that high because it's not being released from that high of a height, right? If I release it up here at like top of the head level, then it's going to go and it's going to probably go to a greater absolute height above the ground here because I'm releasing it from a greater absolute height above the ground, right? It's already kind of starting out with an advantage. My goal is to maximize the potential energy of this thing when it gets to the top of its flight there, and it's going to have an advantage there if it's already starting out when I let go of it with a lot of potential energy, right? So if I release it right here, then it's starting out with a pretty low amount of potential energy. If I release it up here, then it's going to start out with more potential energy. So it's already kind of starting ahead. It's already got a little bit of extra height from that extra potential energy that I gave it by moving it up like that. Okay? You could also think of it as if I release it oriented like this, then its center of mass is right about here. If I release it oriented like this, then its center of mass is right about here. Right? So already I gained a few inches of extra height without even changing the height at which I was releasing the object from. Okay? So in general, the more potential energy you can start the jump with, or in this case the throw of my charger, the greater the height, all of the things being equal, you're going to get to simply just because you're starting with an advantage. You're starting already at some height above the ground. Okay? Now, what about the other piece? What about the takeoff velocity piece? Why is that a factor? If I hold everything else equal, right? If I release it when it's in the same pose here from the same height, the faster that it leaves my hand, or the faster velocity that it leaves my hand with in the vertical direction, from the impulse that I generate against it with my hand, with my throwing action here, the higher it's going to get. And why is that exactly? Well, it's going to leave my hand and it's going to have a certain amount of velocity. And once it leaves my hand, then the force from my hand is no longer acting on it, and the only force acting on it is gravity, pulling its center of mass down like that. Gravity is, at least on most places on planet Earth, is negative 9.81 meters per second squared. And what does that number mean exactly, 9.81 meters per second squared? You can think of it, or negative 9.81 meters per second squared. In this context, for something moving vertically against gravity, I like to think of it as gravity is going to be slowing you down in that vertical direction by 9.81 meters per second. Okay, that's what 9.81 meters per second squared is. It's 9.81 meters per second. So every second that this thing is airborne and is out of my hand and only has gravity acting on it in the downward direction, gravity is going to be accelerating it in that downward direction by 9.81 meters per second every second. Okay? To keep the math easy here, let's just round up and let's pretend that gravity is negative 10 meters per second in that downward direction. So if this thing leaves my hand at a velocity of positive 10 meters per second, then how long is it going to be airborne? It's going to take it 1 second to get up to a velocity of 0 and reach its peak height and start falling back down, right? So in that case, the peak height is dictated by how fast it was moving when it left my hand, because that's going to dictate how long it takes for gravity to take all of that kinetic energy away and convert it all to potential energy here at the peak of the height, right? You can think of the point at which you get to the peak height as being the point when all of that initial kinetic energy has all been converted to kinetic energy, or sorry, has all been converted to potential energy. So at the peak height, instantaneously, this thing has a vertical velocity of 0. It's not moving upward, it's not moving downward, just instantaneously, it's just hanging there in the air for a brief second, or a brief fraction of a second, really, until gravity starts pulling it downward back towards the Earth. Okay? So it leaves my hand, and it has a fast initial vertical velocity, but every moment it's in the air, gravity is gradually taking that kinetic energy and converting it, slowing it down and converting it to potential energy. And when is it at its peak height? Well, that's when gravity has taken away all of that initial kinetic energy, and now it's all potential energy. Okay? So the faster that it leaves my hand, the longer amount of time it's airborne, the longer amount of time it takes gravity to convert all that initial kinetic energy to potential energy, the higher it's going to get, because there's more kinetic energy to begin with to become potential energy, and the higher eventually the height it's going to get to. Okay? So, for example, let's suppose it leaves my hand with a initial vertical velocity of 20 meters per second, and gravity is negative 10 meters per second. Then in 1 second, it's going to be at a vertical velocity of 10, and in 2 seconds, it's going to be at a vertical velocity of 0. So that time, since it left the hand twice as fast, it took twice as long for gravity to take all that energy and all that velocity away and convert it to potential energy. Okay? So if you want to throw something high or jump something high, like your body mass, you want to leave the ground with the greatest amount of potential energy already and also the greatest amount of kinetic energy. So from a kinematics perspective, you want to leave the ground with your center of mass already as high as possible. This is why tall people are generally good jumpers. And you want to leave the ground with the greatest velocity as possible. This is why quick, powerful people are generally good jumpers. So what does all this stuff I'm yammering on about here have to do with arm swing? Well, from one perspective here that I've been giving you at the center of mass level, in order for arm swing to increase how high somebody jumps, it has to be doing some combination of these things, right? One or the other, or some combination of both of them. It has to be increasing the impulse generated against the ground, which would increase my takeoff velocity, increase my kinetic energy, or it has to be increasing the height that I get to, or the height of my center of mass at the moment that I leave the ground, which is increasing my initial potential energy. Some combination of those things. Okay? This paper is a nice example of examining which, if either of those particular things is going on when people swing their arms and jump higher than without swinging their arms, and also examines it at a finer level of detail, examining what happens when we swing our arms at the level of the individual joints. So rather than looking at the whole body, looking at the mechanics also at a smaller scale of detail, kind of one level of detail down from the whole body level, and examining at the individual joint level what are the mechanics of the individual joints, the hip and the knee and the ankle and the shoulder and the elbow, the main arms of the or the main joints of the arm, in terms of their sensitivity to swinging the arms versus not swinging the arms. Okay. This is a good example of something that you see in sports science a lot, where it seems like a pretty simple, pretty straightforward question, right? When people jump, there's a diagram down here. When people jump while swinging their arms versus jumping without swinging their arms, why do they jump higher? What are the mechanics there? Seems like kind of a simple question, but it turns out, like many cases, that it doesn't have a simple answer. They illustrate here at the beginning several theories on why arm swing is suspected to increase jump height. and they give some kind of a historical perspective on evidence for and against various theories, both in terms of theoretical arguments and data from studies and whatnot. And then it turns out that, and this is kind of the take-home message in their abstract here, it's concluded that none of the prevailing theories on their own can exclusively explain the increase in jump height when their arms swing. It rather seems like it's some combination of several of these mechanisms or several of these theories all acting together to kind of in synergy to increase the height of the jump. So more complicated in reality than it might seem on the surface. Not any one single thing that seems to be explaining the increase in jump height when people swing their arms versus not swing their arms. I think I actually forgot to introduce the paper here like I normally do. This is a 2004 study in Journal of Biomechanics, which is kind of the main field-specific journal of our field, by Lees et al., and titled Understanding How an Arm Swing Enhances Performance in the Vertical Jump. Unlike the previous two studies, this was an experimental study, an experiment on human participants, where they measured biomechanics of individuals jumping with and without swinging their arms, and then did some model-based analyses of those data, not simulations of the data, but model-based analyses of the data to determine the work done at the joints and various other elements of interest to kind of reason out why the jump height was greater when people swung their arms versus not swung their arms. Okay, one thing that I did that I added to the paper here is that if you take the data that they report on the participant characteristics and on kind of some of the key outcome variables here in tables 1 and table 2, you can calculate what happened in terms of the impulse momentum relationship, which they don't really present directly in the paper or talk too much about. But I went ahead and took the data that at least the averages they reported and estimated what was going on there in terms of did the force increase or did the time increase. You can see in, I believe, table 1, table 1 at the bottom, and the very last row there on table 1 where it says duration of action, which is the amount of time that they spent on the ground performing the jump before they became airborne. You can see that they were on the ground for 0.96 seconds on average for the arm swing, which is pretty typical for a counter movement, and 0.86 seconds with no arm swing. Okay, and that was a significantly greater amount of time spent on the ground with arm swing than without arm swing. And they don't really make a big deal out of this in the paper, but again, from our simplest model here of what's affecting jumping, this takeoff velocity issue from the impulse momentum relationship, this suggests that if they jumped higher with arm swing, which they did, their subjects jumped quite a bit higher when they swung their arms versus not swung their arms. They were on the ground for about ballpark 12% longer duration of time when they swung their arms versus without swinging their arms. From those data, you can back out here what the average force, let me make that a little bit bigger. Yeah. From the data reported in the study, the body mass with and without arms, which is the same, it's the same people, the takeoff velocity with and without arm swing, and the duration of ground contact with and without arm swing. From the impulse momentum relationship, you can back out what was the average ground reaction force, or what must the average ground reaction force have been when they swung their arm, or when they jumped with and without swinging their arms. When they swung their arms, it was about 960 newtons, and when they didn't swing their arms, it was 966 newtons, which I can't calculate individual level results for this. This is just an average result, so I can't run any stats on it. But I would be stunned if that ended up being a statistically significant result. So you'd probably conclude that swinging the arms did not increase the average force they generated, but it did allow them to generate that average force for a longer amount of time. Okay. So this in context with the previous study where we observed people spending more time on the ground using the counter movement jump versus the squat jump to execute that typically more higher performing jump, kind of seems like we're observing a general trend here, where if you want to jump high, you want to spend as much time on the ground generating your average force as you can. So just spending a lot of time on the ground is typically a good thing for the goal of jumping as high as possible. It won't necessarily be a good thing for trying to accomplish other jumping specific sport relevant goals, like jumping as fast as possible or getting to a certain height at a certain time, like timing or being able to land in a certain spot. So not that you always want to spend as much time on the ground as possible. That'll of course be a case by case thing. But to jump as high as possible, we seem to be kind of observing a trend here that if you want to do that, spending a lot of time on the ground, generating as much force as you can is probably the way to go. Okay, now more specifically here, what happened when the individuals swung their arms versus not swinging their arms. You can see here in table 2 they swung their arms and increased their potential energy at takeoff versus not swinging their arms. 1.37 joules per kilo of body mass versus 1.14. They also increased their kinetic energy at takeoff, 3.95 joules per kilo versus 3.33 joules per kilo. Okay? In units that you guys may be a little bit more familiar with, here on table 1, they have those energetic results converted to kinematic results. Okay? So when they took off from the ground, they were 14 centimeters already. When they swung their arms, they were 14 centimeters above their standing center of mass height when they swung their arms, when they took off. And when they didn't swing their arms, they were only about 12 centimeters, 11 and a half centimeters above their standing center of mass height when they took off from the ground. Okay, so about an increase in ballpark 2.5 centimeters of height already at the instant of takeoff when we were allowed to swing our arms. Then they also took off with a velocity of 2.81 meters per second versus 2.58 meters per second, which may not seem like a lot, but that's actually a pretty appreciable difference in velocity for something like this. And remember that velocity, if I go back to my equation here for peak height, that velocity gets squared. Okay, so even a small increase here in velocity is going to be a proportionally large increase in the peak height that I'm going to end up getting to. Okay, so more interestingly and more kind of along the theme of our class investigation here, why do these things increase jump height? Or what was it about arm swing that allowed me to take off at a greater height or to take off at a faster velocity? And I'll pull up my video here to demonstrate this. The takeoff height is pretty straightforward and is pretty obvious to demonstrate here. I'm going to have to duck down here to fit onto the screen. But my center of mass, when I'm sitting right here, is roughly in the belly button region. It's a little, few centimeters or a few inches above my hip here. But my center of mass is not fixed in that location, right? The location of my center of mass depends on how the masses of the individual parts of my body are arranged around that center of mass, right? Like I can move my center of mass forward here by leaning my trunk forward. Like right now, my center of mass is probably about here out in space somewhere where my right index finger is pointing around here. I can move my center of mass forward by flexing my shoulders up like this, right? That takes the mass of my arms and moves it forward, which is going to move my center of mass forward. Importantly, for jumping, it's also going to raise my center of mass up because I raised the center of mass of my arm up. Right? And then if I keep raising the center of mass of my arm up and do it with both arms, so doubling the mass there, that's going to increase the height of the center of mass even further. Okay? So without arm swing, with my arms just fixed in some pose, then the center of mass of my body in terms of how it's influenced by the position of my arms is just a fixed constant thing, right? Whereas if I'm allowed to swing my arms, if you watch what people do when they're trying to jump for maximum height, they tend to swing the arms all the way up in the air like this. Okay? And what's that going to do? Well, when I take off, that's going to start with my center of mass already as high as it can possibly be, at least in terms of a function of the position of my arms. By raising my arms up as high as I can get, I'm raising my center of mass up as high as it can get, at least at that point in time. Okay, the trickier bit here is why exactly does swinging my arms increase the velocity of my center of mass at takeoff? Here, I think they make a pretty compelling case that this was resulting from increasing the work that was done at not all of the joints, but at most of the joints, in the direction of raising the center of mass, okay? Or in the direction of performing work on the center of mass in the vertical direction in order to increase its kinetic energy at takeoff. Okay? That's shown here in Table 2, where they say WD+. This is positive work or work done in a certain direction of the joint or in the positive direction at the joint, increasing the total energy of the joint at the ankle, at the knee, the hip, and the shoulder, and the elbow. Okay? For the ankle, you can see here 2.06 versus 2.03, not much going on there. Knee, 1.94 versus 1.94, not much going on there. But at the hip, we saw a pretty big increase in the work done at the hip in the positive direction when people swung their arms, and also, as you might expect, pretty big increases in the work done at the shoulder and the elbow. Okay, these latter two cases here, the work done at the shoulder and work done at the elbow, that's kind of natural, because with the no arm swing, you're not doing much of anything there at all, practically zero work done at those joints, and when you're allowed to swing them freely, you can then increase the work that you do. But by swinging the arms, I was able to get an increase in the work done at my hip joint here by swinging the arms. Now, why is this work done at the lower limb joints important? Let me pull that up here. Okay, notice here that, and I'll just start in a squatted posture here. My positive directions here for work, like for my hip, is going to be this direction. So imagine like firing up my glutes to increase my hip extension moment here and kind of extend my hip backwards like that and point my trunk up in the air like that. Okay? When I do that work on the hip, when I do that positive work on the hip, concentric work with my glute muscles, that's going to tend to pull my trunk up in the air like this, and that's going to raise the center of mass of my trunk up in the air as I rotate the trunk back like that, and through that going to raise the center of mass of the entire body. Now, if I'm doing this dynamically in a fairly short amount of time, I'm producing that work quickly, I'm generating a lot of power, and that's going to translate to a lot of speed of the center of mass in the vertical direction. So kind of an explanation for why I'm getting that increase in height just from extending the joints like that, and also why I'm getting a faster takeoff velocity. So more work overall done by the arm joints, of course, but also by the hip joints in order to increase the takeoff height directly from the actual motion of the joints, but also from translating some of that extra work done at the hip joints and the shoulder and the elbow to increasing the kinetic energy of the center of mass in the vertical direction at takeoff. Okay, if you're still not satisfied there, another factor here is kind of, we're kind of always saying why here at continued levels of detail. Why does swinging the arms allow my glute muscles to perform more work on my hip and then increase the energy of my center of mass? That's a great question. They do some kind of speculative analyses of it on here. I don't know with a study design like this if you can kind of definitively answer that question. One key here, I think, and something that they highlight, is that if you look here in Figure 1, the part here highlighted at like 68% of the motion in the arm swing and 67% in the non-arm swing, that's the peak depth of the squat there. And you can see here the orientations of the shank and the thigh are about the same with and without arm swing, but the trunk is leaned over quite a bit further when they swung their arms versus when they didn't swing their arms. One thing that's going to do is, among a number of things, that is stretching your hip extensors more, so possibly stretching them up to stronger places on their force length curves, and also, if you're doing this fairly quickly, stretching them faster and stretching them up to strong, powerful places on their force velocity curves, so possibly helping you there generate more work at the more work and more power at the hip joints there, and increasing the height and the initial velocity of the center of mass by swinging the arms backwards like this and helping the trunk get pitched forward further there. Okay, that is it for today. We will see you next time.